Going live, I think. Hello, Maths2222 in chat. I'm starting the live stream, is the phrase that I've been told to say at the start of these. Today, Pell's equation. It's semi-famous. We're going to learn about it in this textbooks that we've been reading, which is Hatcher's Topology of Numbers. We've been looking at a lot of continued fraction facts, and it is time to look at an application of those to equations of this format. I'm excited because we've got a few pages of this and then the legendary chapter 5 where everything is actually proved. Lots of times in chapter 4 we've been frustrated by the fact that the book says next chapter's got all the proofs of these facts in. So possibly if I charge through this introduction to Pell's equation, possibly I can charge through and get really stuck in chapter 5. Hope you're doing well, everyone. Hi Mary, how are you doing? And if I missed anyone else, no, that's chat. There we go. Good to have you with us, everyone. I am going to try and launch, I think, because, yes, I've got 2 weeks off after this for various Eastery sort of things. A bit like how my professional live stream is also taking 2 weeks off. This is the unprofessional one. I got a comment on YouTube. I got a comment on YouTube of someone asking, is this helpful for the mat? And almost intentionally no. This is my chance to talk about anything that is not on the mat, except awkwardly equations like x squared minus 19y squared equals 1. I have used that in my professional life. It's the same maths at times. Right, good, but almost intentionally unhelpful. If you've come here to learn about the maths admissions test that I'm involved with for work, bad news. I'm just learning maths myself over here. This is just me doing other stuff. Right, good. It's quite a scary comment. Gets me if the cat fractal would be terrible, wouldn't it, for work? I've tried to label them on Twitch. If you're on Twitch, there's a description thing that says that I do a professional live stream for work and I do an unprofessional live stream here. We will separate the personas out. Maybe I'm just a different person who happens to have the same name. Good, right, yes, I'm all right. Let's get going then with some Pell's equation. Here we are. It's this equation, which we've seen briefly in chapter 0, way back at the start of the new year, when we took on what's turned out to be a kind of New Year's challenge, I suppose, to work through this textbook. How's it going? It's going all right. Chapter 0 had this equation. We're not going to worry about d being square because then you can do difference to squares, factorize it, find the solutions. But as an example, we're going to look at this with 19 in here, which maybe have used in some sort of thing. I remember the numbers 170 and 39 coming up. Anyway. So there's this thing called a periodic separator line, which works by, there's a complicated diagram, it's on the front of the textbook, it's turned up a few times to think about the values of this as you plug in all of the values, all of the possible pairs x, y. So you plug those into this expression, you get lots of different things. You could try random numbers, but there's this way to work sort of systematically in the book, where you start with 1, 0 and 0, 1, which for fraction reasons that I'm not entirely a fan of, you could write those as fractions. This one makes me feel uneasy things. But you could plug in 0, 1 and 1, 0, and then the rule could be that you take the points you were looking at and you add them together. And you replace one of the ones you were already holding in memory with the sum. You can choose which one to overwrite, so there's a kind of binary tree of places you might go with this process. Do you replace the thing that you were holding in your left hand or the thing you're holding in your right hand? You add them and that replaces one of these fractions or vectors or whatever. You can store it here or you can store it there. The surprising fact that this book really relies on is that as you keep doing this, you visit every coprime pair of points x, y exactly once. So if you only care about coprime numbers, either because they're fractions or because, well, a common factor here for x and y would ruin us because it would be a multiple of that common factor on the left, certainly not on the right. So if you only care about coprime x and y, then you can sort of store them in this enormous binary tree of vector pairs, which is sometimes called the Calkin-Wolf tree. I think might be actually I should check. I should fact check that. There is a thing called the Calkin-Wolf tree. Is it the same as ours? Yeah, it's definitely this, isn't it? Yeah, I'm pretty sure it's this. The Calkin-Wolf tree, which I've hastily Googled. Yeah, it's about adding, right? Oh no, but this only has one parent. Ugh. Okay, maybe this is different. I take it back. Right, I was in flow though. You search through the binary tree. You search all the points. In particular, if you look nearby the ones where you're getting either positive or negative values, you're looking for quite a small value here, number 1. If you're looking nearby, then you have this kind of separator line in your binary tree, separating out points where you get positive values and points where you get negative values. This has then been straightened out, so this is part of a binary tree. It's got lots of things of degree 3, but being straightened out as we walk through this binary tree. It's infinite, it keeps going, so it keeps going. Surprise, which is going to be proved in chapter 5 when we get there, but this thing is periodic as you head towards square root 19, working down this separator line. The sequence of branches, not the numbers, literally for the values, but the sequence of numbers is like that. Hello, Mimachine Rex. You all right? I hope you're doing well. Good. Right. Maybe my favourite sentence of this book so far is ignoring the label 741 over 170 for the moment. We will come back to this label 741 over 170. The other fractional labels, the first few conversions for the continued fraction from root 19. I suppose so. Root 19 is about 4, but not quite 4, it's 1 over 4. So we had this other thing going on where the number of branches left and right are they the numbers in the continued fraction? I think they might be. So this is sort of 4 on the right, and then 2 branches on the left, then 1 on the right, then 3 on the left, then 1 on the right, 1 on 1, and then loads, which corresponds to these numbers in the continued fraction. We've seen that if you like, it's your choices about whether you add, and then you replace it either with the thing you're holding in your left hand or your right hand. That's your choice. So if you make this choice 3 times, you end up with the number 3, and then you start making maybe some choice on that side. We haven't proved it yet, but periodic continued fractions correspond to roots of quadratics, which again is in chapter 5, which is only a few pages away, so maybe we'll get there today. That's my aim. Reading maths is difficult, reading maths is very, very slow. Right, okay. Twitch is telling me strange things. I'm going to ignore Twitch and just learn some maths quietly. Let's go. If you're new to this Twitch channel, hi. We're trying to just learn maths, and some of the Twitch stuff is useful for that. Really do like live chat, that's great. And some of the Twitch chat, adverts, raids, is I haven't worked it out yet. Good. Right. Okay. Versus on the zigzag path, infinite string of triangles. That's the thing I was thinking of actually for our continued fraction, which you can superimpose. Last week the book did a kind of switch on me and started talking about the lines between things rather than the lions connecting things. No, there's no lions. There could be. So you need to imagine that there are lions who live in each of the regions. Cute little lion, there you go. Really big mane. And they could be joined up by lines, which is what I meant to say, to the lions in the other regions. It's important not to confuse the lines with the lions. They're kind of the dual graph, whether you have these as the points or these kind of vertices as the points instead. Right, good. I should probably draw one of these little fellows in each of the regions, I suppose. It's connected to this one over here, for example. There's this kind of dual graph. A dual graph means that you put a vertex where you had each region and you connect them if there wasn't an edge, a neighbouring, if they were neighbours. I've seen this stuff with maps where you want to do a map of you're trying to learn which countries border each countries. So you do a map where you have like a blob for Germany and you connect it to Germany's neighbours and so on. maybe you're making like a Ticket to Ride kind of board game or something, and you have nodes for different countries. And this graph that you get is totally different from the graph that you get if you just drew like an area for Germany and marked in the boundaries. It's kind of a different graph for boundary points. Anyway, right, I found good. What are we doing? Well, so why is that one not a continued fraction thing? Why are we ignoring it? Not sure. It was going quite well, wasn't it? I think this is the next one. If not, I don't really know what's going on. Region value of the form. Oh, right. Hang on. We're interested in this one because the value has got back to being 1 again. We're going to prove later that these things are periodic, and when you plug in 1, 0, you get 1. So at some point after a periodic string of triangles and lions and things, you get back to the number 1 again, which happens here. Wow. So this tells us something like this, which at the moment is magic because we haven't proved that it's periodic, and the numbers in the middle here have been calculated for us by the textbook. So this is not even possibly just to play along. I should like fact check this or something with a handy calculator. Right. Okay. What am I looking at? 170 squared. It's 28,900. It's quite a lot. 39 squared times 19. 9 times 19. 28,899. Yeah, okay, fine. That checks out. 28,900 minus 28,899. All right, okay, pretty cool. Good. Yeah, exactly, Rex. If you're doing a kind of traveling salesperson thing with regions that you need to visit, then it's not so much the boundaries between regions that interest you, it's the lines connecting regions. If the lions are all in a zoo, then it's the difference between the fences that might be keeping them apart and the friendships that they make with their neighbours. Right, okay. The important thing is that I'm having fun. What have we got? 170 over 39 is the value of the initial portion of this bit without the 8. Because, right, oh my goodness. So this is telling us that you get round to the bit where it starts repeating, and halfway through the repeating, there's this number 1 for this big region up here. Yeah. So it's sort of the corresponding stuff is the 4 at the front, which is half of the 8 because we're halfway through a kind of repeating block. There's some symmetries going on. We haven't proved them yet. And then there's all these kind of repeating numbers corresponding to the repeating sections. 2, 1, 2, 3, 1, 2. It's 1, 2, 3, 1, 2, and then 8. That's before that then. Right, so after the 2, we get to, in our triangle model with all the lions, we get to this region, which is the region labelled 1, so that's the one we care about. So it's just before this kind of long section, which would correspond to us starting again. So the periodicity is linked to everything. The fact that it's periodic means that it's not going to repeat, it's going to do it again. We'll get 1 back again. So that gives us a kind of transformation to find another solution. So if we can work out the length of this and all the numbers in it, then we can work out a transformation to get another solution. It says look over here, right? Eventually this will happen. Oh, and I might care if it was 1 down here somewhere, because that would be a kind of, another solution. That'd be a kind of glide symmetry. But I suppose this is the separator line, so it's positive above and negative below. So that's not going to happen. Okay. I care about -1. Maybe not. That's an interesting question. I think it has to give us all the solutions if the separator line is like a real thing. If the separator line is a line separating out places where this is positive and negative, then any place where its value is 1, oh no, is this true? I was going to say would be surrounded by, oh yeah, because the alternative is it's surrounded by that region would be maybe surrounded by things where the value is greater than 1. That's not obvious, but I reckon the textbook is going to tell us that style of thing, to say if you have a region where it's 1, then there exists at least one region nearby where it's negative, so the separator line will go straight past this region and it'll be included. That's my guess for how the proof is going to go. I think it's a good question. How would that work then? How would you force this to be negative in a neighbouring region? If you have... Oh, I don't even know what the neighbouring regions are. Do I? Maybe I do. Maybe not. We have this arithmetic regression fact. Yeah, no, at the same time, good. There's an arithmetic regression fact, right? Feels like that's gonna. We've proved that for a reason. Is it gonna come up as if you have the number 1 somewhere? I'm hoping that you can force. So I don't know anything else about what's going on in this binary tree, but I'm hoping you can force there to be some negative numbers somewhere. Yeah, so it's something like suppose for contradiction that all of its boundary is positive numbers, then so the boundary around 1 is actually infinitely long, but whatever. The boundary around any of these regions is really long because these are the kind of trunks of more binary trees. Everything's binary trees, so it keeps splitting off. So the boundary around this thing's infinitely long. If you had somewhere a value which a region where it evaluated to 1, then maybe around all the sides it would be positive numbers. But we've got a rule about arithmetic regressions, right? Let's see, how does this work? So if I have like ABC or something around here, I think it's like A and then to B plus 1 to C. So there's something like A, B, C are almost in arithmetic progression, but not quite. These are the numbers along the bottom here as well, by the way. There's kind of thing going on. Maybe we could analyse that sequence where each one C, A, B plus 1 and C are in arithmetic progression, and then so on. So that tells me something about C in terms of A and B, not quite that they're in arithmetic progression around the edge. Maybe we can use that to prove that the numbers dip down to be negative. There's this kind of quadratic thing going on, right? I know it's all quadratics. 1, 4, 5. What is this? So this is like minus 18. So if I look at reading across ABC or something, I think I can go in either direction. Yeah. The thing I observe here is that it's going down and up again. It's got this kind of maybe parabola shape, possibly hyperbola, whatever. I'm going to solve this, I think, and then prove that it can't be all positive numbers all the way around. Doesn't sound that plausible. Seems like there's a minimum here, and then it'll be symmetric around the other sides. Why can't that minimum just be a positive number? Let's find out. So if you have A, yeah, okay. This is probably good for me. I probably should do this. Maybe I don't understand this fact though. So minus 19, minus 17, minus 15. Okay, so it's A and then this plus 1, it's minus 17. That's the middle term of the arithmetic progression. And then the next one is minus 15. Then you read it again. You go minus 18 on the left. 1 plus minus 15 is minus 14. So then the next thing might be minus 10. And then you keep going. So minus 15 minus 9 is an increase of 6. So the next one, minus 15 minus 9 is an increase of 6. I think I'm expecting minus 4 or something. Shouldn't it be minus 3? What's going on? What's going on across here? Minus 10. Oh, something weird's going on. Something I don't quite understand. This one, some of these, that one? No? Let's get rid of that exclamation mark, it's annoying me. Minus 15, minus 9 for the ones across the middle, and then out the other side, shouldn't there be minus 4? What have I got on here? I've got over here, I've got -3. Well, I wanted to be -3, but I can't make the numbers work in my head. I'm struggling to explain to myself why this is a sequence. Yeah, I'm just an idiot, right? I need to add 6 to -9. Yeah, okay, good. I'm happy. I can't add, that's the problem. Sometimes you've got to follow these, because it might be the case that I'm misunderstanding something, but no, I just can't add. Ah, dear. Yeah, thank you. Yep. I'm up to speed now. -9 plus 6 is -3. Good. More seriously then, so what is this? We could play this game with positive numbers though, couldn't we? And we're about to. So maybe I could show that if A and B, yeah, okay. So suppose you have A and B. Suppose you have A and B, both neighbouring the region 1, with, let's say, A and B both positive for contradiction, and A greater than B without loss of generality. Yeah, because I'll just read the argument. The thing is symmetric, I'll read it left to right or right to left, whatever. This is going to say reading in the direction where they're decreasing. My aim is to show that it keeps decreasing. So then either you get a negative number and you've found the separator, or you have another positive number and you do it again. So my aim is to show that this thing is less than B. Aim is C less than B. It could be negative, in which case we're done, or it could be positive, in which case run it again. You can only do that finitely many times. Seems true reading down this side that this will be the behaviour. Let's see if we can prove it. We have this, which should hopefully be straightforward. Oh no. There's an arithmetic regression going on. B plus 1 minus A, the difference here, is equal to C minus B plus 1. Sorry, you have to look at the top of my head quite a lot on this live stream. Let's try putting it here. Okay. So, what have I got then? I'm trying to solve for C. So that says 2b plus 1, 2b plus 2, plus A minus A. Oh my goodness. 2b plus A. No, come on. So C is equal to, I'm getting there. 2b minus A plus 2, which, I was hoping that would be obviously less than B. Let's just write it down optimistically and see what happens. Is less than B because, totally how maths works, right? B plus 2 is less than A? Question mark, because I'm not sure if I believe it. That says if they differ by at least 2. So if I had that as a hypothesis at the top, if B was actually quite a bit less than A, then I'd be happy. I'd be done. I don't understand why that would be true though. So I can put it up here as a condition to make this true. A greater than B plus 2. Up here, and now it's all true. It's no longer really log, but otherwise I'm worried that C will be, well, look, precisely if A and B, if they're the same number, that can happen, sort of, sometimes. If they're the same number, then you get C larger on the other side. In which case, maybe I want to look. Yeah, so you get cases like this where it's 9, 9. If it goes down. Well, never mind. Okay, something like this. Find the quadratic sequence. Yeah, do that. Find the quadratic sequence and check what's going on. That sounds possible. Is it a quadratic sequence? I said quadratic sequence out loud, but that was kind of bluster. Oh my totally. Yeah, no, I'm happy. That's a quadratic sequence. Pause check. Quadratic sequence, there's a load of quadratics hanging around. X squared minus 19y squared. What are these things going around the outside? Where did this rule come from? Ah, it's a median thing. Once you know one of these, the rule for the other ones comes from the fact that they are, in some order, the medians and the kind of difference version of the median with a minus sign in there. The thing that created this. You know you're in a binary tree, so there's some direction to the binary tree that you can impose on it. Yeah. So this quadratic sequence has got a kind of second difference thing. Is this going to be related to this number 2 for the kind of differences for what's going on? So that makes me think it's a quadratic, sort of happy quadratic. But then understanding why the minimum of that quadratic, it now feels kind of consistent that it could be just any quadratic sequence with a unique minimum, like 1 or something, or 37, that then read around would be okay. Like this, I think nothing wrong with this. So 37 and then add 1, 38. So I get up to it on both sides. Yeah, so I can't ban this, I think. 37, 39, and then the next thing would be 37, 39, 41. So, like this sort of sequence. Uh-oh, that would be a place where it's 1 surrounded by this quadratic sequence. So I think I need to actually delve into, if I want to prove this, it's maybe not enough to just use the facts that we've got. Yeah, so it's a happy quadratic, but it doesn't tell us the minimum. It doesn't tell us whether it crosses the x-axis. Science. Yeah, I should have thought that faster, that I could just add a constant everywhere. Is there anything I can do? No, that really could happen in theory. I think it doesn't. I think this method is going to give us all the solutions. But we could have, the number 1 surrounded, but in theory, at the moment, for me at least, it could be surrounded by quite large numbers. Just 50 odd larger than the ones down here, because adding a constant's fine for a quadratic sequence. Okay, fun. Good side investigation. It's nice to not understand things because that gives me more of a reason to read the book. Let's try that. Okay, so final term omitted because there's some stuff about it starting to repeat in here. You have to wait for it to. Once you get here, you're kind of done. But you have to wait for this bit before you can get going again with the next bit of continued fraction or something. Okay, this is the kind of point at which it starts repeating in the middle. There's 1 and minus 19, and then it all repeats. You can't wait for that to happen. Okay. Right, okay. Infinitely many solutions. Towards the right. Okay, you can write down transformation. Excellent. That's how you get to the next one. Here are the numbers. Get a larger and larger infinite sequences. Solutions, yep, great. By applying this matrix, the one that takes you directly to that point over there. And there's a good one. Okay, now they're saying next. But we're not yet convinced that we've got all of them, because there could be a region somewhere else where the value is 1, but surrounded by a shield of large numbers, so we're not looking over that. Right, okay, now it's pointing at various things going on in this matrix, fine. 2 170s, yeah. 741 factorizes as 19 times 39, which is fine, 19 times larger than that one. Is the discriminant of this? Oh, this is like the original solution that we found, non-trivial solution. Right, okay, well here it is in general. So found the first solution to be this. Based on the previous example, we suspect that the periodicity transformation is this. we're going to check that it works, but what's the reasoning here? Something like, wait, we know what's going on once we've got to the periodic bit, right? We know that we've got. We know there's a minus 19 down here, so we know that these things have x squared minus y squared equals minus 19, I think. Maybe that's relevant. That's where you might be getting a minus 19 from, like in the pattern. Good times. Let's have a look. So if you get all the way through to PQ as a solution, then I guess my question is, what's opposite that in the middle? What's on the other side? And it's not obvious to me at all what's opposite that. No, not obvious. I've been told to ignore the numbers 741 and 170 for now. I'd like to understand where they come from at some point, or how we calculate them as dq and p. So these numbers are secretly multiples of the ones we had before. The determinant is this, which is positive. Yep, okay, so I thought they were going to tell me this. As we move along the separated line. So, what's going on? It's something like... So I've seen these Pell equation things written out before as something like, what do? You want x squared minus 19y squared? X squared minus dy squared, or something in general. Which you can do by having some matrix like this, that you put x, y into on the left and the right. Oh, I said left and right the wrong way around. Good. Putting x, y on the right and the left, that gives you x squared minus dy squared. So possibly what we're doing is finding a transformation. How does this work with the transformation? So if I give it t xy instead, then I'd quite like it to be the case that t transpose, maybe? I regret using t. So some m for does mx work is something like the question. So if x is a solution to this, then the value would be 1. I'd like to know, does mx give the value of 1 as well? So I'm kind of interested in whether this expression equals 1. Yeah, not obviously. The proposal is that we use PQ DQP in columns. So this expression is checking that that works. I wish there was an easier way to say that with matrices. So it's like the opposite of diagonalizing the matrix, right? I've got a nice diagonal matrix, and I would like to do some weird change of basis to it so that I end up with a... I don't know what I'm trying to do. So that when I give it a different value of x, it's all okay. Does it? Yeah, so it's kind of already diagonalized, right? It's my one trick. So this calculation on the right here is trying to convince me that this matrix calculation in the middle, which they've written out as a scalar when the dust settles, right? Oh no, it's a matrix. They're trying to convince me that this matrix is, I think, 100 minus d, which is slightly better than proving that when you put the vectors in, you get the right thing. It's kind of equivalent. Everything's symmetric, but it feels slightly better to do it with the matrices. I'm going to give that a go quickly down the side. I think I don't know. I think that sometimes doing these things is helpful. Maybe not, because I've now got to multiply some matrices together, and we know how that goes. Right, so let's go then. So this is going to give me PQ, DQP on the left, and I'm going to multiply this pair together to get P and then minus DQ, and then DQ and minus DP on the right, I hope. And then I'm going to multiply out. So we're using the fact I hadn't appreciated this. PDQ minus PDQ, PDQ minus PDQ, and then down here we get D squared Q squared minus PDQ or something. Or something, it says. Willing to be wrong. D squared Q squared, oh yeah, okay, minus DP squared. So using the facts that p squared minus dq squared was 1, that's 1, 0, 0 minus d. I got scared of all the extra factors of d down here, but we're all alright. Good morning, Sanitation Black, how are you doing? Or good afternoon, I suppose, depending on time zones. Yes, good. So that gives us the same matrix. I prefer to do that as a matrix calculation, I think. And then when you put the x and y's on both sides, it gives you x squared minus dy squared. So what are these? I really think this matrix has determinant 1 and the eigenvectors. So this must be some sort of... What's going on? What's going on with this matrix? So we're diagonal before and we've stayed diagonal afterwards. Yeah, I can't remember enough group action stuff to work out what we've done. But something like we've done some action on... No, I shouldn't even say group words. Let's not say any group words. Right, good. Good. Determinant 1 I think is not quite enough. Yeah, determinant 1 is I think not enough on its own. This matrix on the left is literally the inverse of this one on the right. That's a sort of related fact, isn't it? Or is it not quite? It's not quite the inverse of the one on the left or something. Yeah, there's missing some factors of D. What is going on with these matrices? Sort of an inverse up to factors of D and possibly minus signs, which makes me suspicious about this. Yeah, the product of these things is not the identity, but the product of these things with this in the middle is that, which makes you think that their product should be the identity. If matrix multiplication was commutative, then it would all be okay. Because you could move the thing and cancel it on both sides, but you can't cancel it out the middle, so I should calm down a bit. Right, okay. I have a matrix as well. Right, okay. There's something going on with matrices here. DQP, where does that come from? Just doesn't say. Right, okay, we're going to move on. Maybe chapter 5 will tell us. Oh, yeah, okay, fine. Probably it's one of those. So these are quite rare because this is going to tell us this is the correct sort of transformation to take us along the separator line. So that's all the way along the separator line. Yep, to get another solution with value 1. Because if you do this transformation to x, then you'll get back to the value 1, and we know that only happens if you go all the way to this, sort of 170/39. So it's quite unusual. It's just that matrix to move along the line, and then powers of that matrix, maybe other solutions hiding out somewhere else. But there's not very many matrices that have this property. I thought interpreting it in terms of matrix properties would be helpful, but I'm realising that I don't really know any relevant facts about matrices. So I'm going to drop that matrix inverse exploration idea, but maybe leave it at the back of my head for a bit. Okay, right, T. That's going a bit cold. We will do our best. Yep, okay, so turning back periodicity again down here. Images 1,0 under this, so powers. Not actually proved yet that the periodic separator line even exists. Oh, right, okay, theorem 5.2 in the next chapter is going to be amazing. Right, here we are. As we will see in section 5.1, next chapter, the values of the topograph with the separator line change in a monotonic fashion. Okay. As one moves away from the separator line. Oh, okay. So this is a slightly different argument to the one I was expecting. This is telling me once you've found the separator line, if you walk away, there's nothing else out there that's interesting to us, which isn't really starting from a proof by contradiction, starting from a position and saying, does this one surrounded by large numbers exist? This is going to say, no, you find all of them on a line, and then as you move away from the line, that covers the whole world, all of the binary tree, there's nothing in there. So it's a slightly different style of proof, just sort of directly, there's nothing out there. Not obvious to me. Yeah, okay, right, good. For an example where this does have solutions. Oh, okay, so now 13s. We'll see in section 5.1 that as you go up the trees, things increase. I wonder if that's obvious. So if you've got two positive values and a negative thing, then at the root of the binary tree, this thing's going to grow like a binary tree upwards. Oh, binary tree. So there's this arithmetic rule which says you've got a negative number under your separator line, of course. You've got two positive numbers, so then the next thing must be positive and larger than even the larger of those two, because yeah, okay, this is a bit better. I stand more of a chance of proving this one. So the number in this case is -4, and then 8 be the next thing to write. No, that's a good challenge, isn't it? The difference between -4 and 4 is 8, so the next term in that arithmetic progression would be 12. So it's kind of an arithmetic progression. The rules for these are you get a number over here, you get x and y in here, and you get b out here. A to x plus y to b is an arithmetic progression. Oops, if that then is an arithmetic progression across one of these shapes. So you have to try and find it in this deformed binary tree, like -4 is to the left of this group of 3, and then there'll be a bit more up here. So proof of that is going to be something like where it grows, you've got positive a and b, you've got some negative number, d, that's negative, and your question is, as I move up this tree, well, this is going to be some large difference or something. So quadratic sequence or something. As you move up, they're all positive. We'll see it in 5.1. It seems more true than the thing I was doing before. Okay. Yep, so for 13 you get the 1s and -1s, that's fun. That one had some sort of glide symmetry to it, maybe? Maybe not. To the lines, the shapes that you got in the continued fraction. Let's find out. This one's got quite a straightforward periodic fraction, or maybe not. 1, 2, 3, and then this one, and then 1, and then there's a dot here, and then 1, 1. So loads of 1s in this one. Okay, what's the dot for? Oh, is it halfway through? Yes, there's a sort of rotational glide symmetry thing. If you rotate around this point by 180 degrees, you get the same picture, because you have these kind of teeth that go over there, and you have all of the next lot going around to here. Oh, and the numbers are negative for each other, aren't they? That's quite nice. I didn't know that. Cool. The values. Huh. So technically all of these regions, as well as having a value of the quadratic form, should be labelled with a fraction. Sort of want to work out the fractions tiny bit. So this is 1, 1, because that's the thing next, which gives us -13 when you plug in 1, 1. but then we keep going. So we keep adding the top and replacing. So 2, 1, 3, 1, 4, 1. Oh, no. There's a line. We stop here. So this line means I was trying to walk across junctions. And the junctions flipped on me and I wasn't paying attention. So after I've walked across, so around this point, I've got 1, 0 in this region, 2, 1 in this region. The right thing to do is to add them to get 3, 1, and I've decided to store it here. But then walking around this junction, I have 3, 1 and 1, 0, and this lineup means that I'm storing it in replacing that one. So I should put the sum 4, 1 up here. So you see I'm adding and then choosing whether I write that, replacing the thing that was above or replacing the thing that was below. So now I get 7, 2, and this line means that I'm storing it below. And then I get 11 over 3, and I'm storing it up here. I hope this is working. Oh my goodness. And then I get 18 over 5, and I store it down here. I get 29 over 8, and I'm storing it, replacing here. I wish they hadn't filled this in because I'm sort of replacing. This is a good tracker of the things that I'm replacing as I calculate along the way. 47 over 13. And then I add that one again to get to, oh good, 65 over 18 for this region right in the middle. And I could keep going. But so this point in the middle, 4, 1 and 7, 2 are kind of interesting to me because they give opposite values. It's really asymmetric, isn't it? Because 16 take away 13 is 3. 49 take away 4 lots of 13 is -3. That's not true. 49 take away 13 lots of 4. It's a bit better. 13 lots of 4 is 52. Cards in a deck. Oh my goodness. Right, yes, more tea soon. Right, now we're going to interpret these. We've got there. It's going to be chapter 5 very, very soon. Here we go. So here's the matrix. I haven't proved this. It's annoying me. We can get to here. What's this in general? The book's got some understanding that this periodicity generally happens to get us. The rule is always PQ, DQ. Oh, no. We have to find the numbers P and Q. You have to do some work. It's not a rule. It's not a formula. You have to do some work and get to PQ. And then somehow magically it knows. The thing on the other side should be DQP. These are the same numerator and denominator, right? That's a periodicity fact, isn't it? That's a periodicity fact. Something like the sequence of choices has got some pattern to it. So those 18s have turned out to be the same. Don't love it. Want to piece the details together, but something like that, I reckon. Right, good. Repeated applications of the glide reflection will give solutions to that. Alternately, very cool. Good. Or if you prefer, ignore all of the -1 solutions. Work out all the fractions along the top. Keep adding and replacing above if it's a up arrow, up line, and down if it's a replacing the bottom one if it's a down line. Keep going until you get to the 1 if you only care about the solutions where you get x squared minus dy squared equals 1. Okay, so we've got to work out how to find this separator line, and we want to understand why it's periodic. That's the challenge for chapter 5, I think. Let's have a quick look at the exercises, but not do any of them because we're too chill for work. This is bad practice. We should really do the exercises. So, for example, what do you even do here? I would calculate the continued fraction, I think, to work out which way the lines go. It seems a bit cheeky, sort of doing it in the wrong order. But to find the separator line, we haven't even proved the separator line exists. So I think I would hope that it exists. Plug into values 1, 0, 0, 1 up. Right, okay, we're off to a good start because we've got a positive value and a negative value when I put in 1, 0 or 0, 1. Off to a good start, and then go from there. Some sort of, yeah, I think we just have to calculate the continued fraction. Could be clever to work out. You could think about left and right. Should I replace the thing on the left or the thing on the right if I want to keep getting something that's the opposite sign? I have to I have to keep doing something. Yeah, let's look up here. Can we explain this in terms of you want to have... Yeah, okay. So the rule should be something like, to generate one of these things, you can generate the lines as well as you go. I've got there. So you get the 1 and the minus 13 for free, plugging in 1, 0 and 0, 1 in this case, with 13. And then what you do is you add the two fractions together that you're holding in your hands. You get 1, 1. Plug those values in. If it's negative, you write this on the right. It replaces that right one on the right. And then you do the thing again. If you get a positive number, which finally happens when we calculate the sum is 4, 1, and plug that in, we get a positive number, and that goes above the line. So you can find your separator line by sort of feeling your way around. Say, oh, I'm on the separator line. I keep going around in this kind of sequence of numbers, which increases quadratically. So you're going to get there eventually, until you get to, whoa, okay, positive number. Now it's time to write that above and do the same thing, looking around until you get to see if you get negative numbers. Or yeah, how does this switchback work? So if you've got a positive number here, you want to add, yeah, you just keep adding, and if it's a negative number, it goes down, and you get this alternating pattern. If it's a positive number, as it is over here, then you write it in. But something like you have an unhappy quadratic sequence, so it can't keep going forever, it's going to come back down again. Is that going to be the proof that this middle one... no, because this could be more complicated. It feels like this was a sort of quadratic symmetry thing going on. Maybe not. Yeah. Well, so they're always, for the ones we're thinking about, x squared minus d squared equals x squared minus d squared, dy squared. There's always a positive value and a negative number, because just plugging in 1, 0 always gives you 1, and just plugging in 0, 1 always gives you minus d. So we always get this starting point for the line. I guess we're also interested in ones where there's some xy term in the middle, and that's less obvious, that your starting values might both be positive. We had some last week where we had to explore and find it. But for Pell's equation, there's no xy term in the middle. And having thought briefly, I wonder if there's a sort of complete the square thing going on, where if you have some xy term, you are looking at some sort of symmetric quadratic form thing. So maybe you diagonalize it. Love diagonalizing. Maybe not, because we're really interested in whole numbers for this book, but it feels like you should diagonalize it. Maybe not. I'll accept that that's a maybe not. Okay. Good, right, okay, so that's how I would calculate, I think, the separator line for this one. I'll start 1, 0, 0, 1 with my values of 1 and minus 14, and then I'll go from there. I don't know if I'm putting the next thing in above or below, but the next thing's 1, 1. 1, 1 gives me up 1 minus 14. Oh, terrible. Oh, I see, so I'm just sort of varying. That's not true. I'm varying both numbers in general. 1 minus 14 is minus 13, so I'll write that in down here. That's 1, 1. The value for 1, 1. And then I'll put it into, yeah, okay, great. And this is going to be, the number of these you do is strongly linked to the value of like the integer part of the square root of 14, and then you keep going or something. That's what we're going to be doing as chapter 5, maybe, in a minute. Oh yeah, keep going until you get to solutions like this, if they have integer solutions. Very nice, you can keep walking and see what happens. Find the linear fractional transformation that gives the periodic transform. Yep, okay. So spot the pattern, continue. Oh, I guess the existence of a linear transform form is going to be possibly our proof that the thing is periodic once we've got one. It sort of keeps happening. Yeah, that's probably roughly what we're going to do, isn't it? No! Ooh. Ooh. This user was flagged as a possible ban evader. Restrict. And ban. Cool. They are getting really good, aren't they? They're using special characters. Although possibly there's some like sweet spot where they have to use special characters that humans can still interpret, but the machine can't. So what we can do is we can either make the machines better at recognizing characters, or we can make humans worse at recognizing characters. For example, if you see any characters that we could go in mode only. Oh well. Yeah, the regex is not good here because it's hard to regex off over everything that looks like an E. Yeah. Okay, well, we'll do the exercises, we'll do T, and then maybe we'll do an experiment. We've got a plan. Determine the integers less than 12. Oh, this is a monotonic thing. Oh, less than 12. So you could, if you found a solution with 1, you'd be allowed to multiply up. That wouldn't be coprime, but you can multiply up to find solutions where it was 4 or 9 by multiplying these by 2 or by 3. That's what it means about not primitive solutions. And other small numbers are going to be near the separator line because it's apparently monotonically increasing. We haven't proved that yet. Do the same things for root 29, okay. I think some of these, let's have a look. There's a Wikipedia page. Some of these are surprising, right? Yeah, here we go. There is a Wikipedia list. I'm happy that I remember this exists. That's a bit small, isn't it? I'll zoom in. We'll go 125. That's a bit better. So x squared minus dy squared, here called n, slightly annoyingly, smallest fundamental solution. So for example, with 5 in there, x squared minus 5y squared has a solution 9 squared minus 5 times 4 squared, because 81 minus 5 times 16 is exactly 1. And there's a really non-trivial relationship between the value of n and the smallest solution that you get. So 13 is an interesting one. Did we see 13? I think we had 13. 649 and 180. Was that in the textbook? Let's have a look. 649 and 180. Oh no. Well, that's minus 1, so you have to do it again. You have to do it again to get through to 649, 180. There you go. So this is a good example because they're surprisingly large numbers. And there's another weird one. So 19 is also fun, which is why it's in the textbook. You get this kind of non-trivial continued fraction that goes on for quite a long time. And then some of them are just really surprisingly enormous. We do love surprisingly enormous pairs of numbers on this Chill Maths live stream. I think Wikipedia told me once, oh, that's just a good number, right? It's just absolutely brilliant that the solution would be slightly more than 500,000. You wouldn't guess it, but slightly more than 500,000 squared minus 89 times 53,000 squared. Like, what's the point of all the zeros? But that's the smallest non-trivial solution. Yeah, good. Okay, there are some patterns here, of course, like 63 being the difference of two squares. That is what's going on, I think. No, that's not what's going on. Quite, I said it wrong. There's some really surprisingly large numbers. Any sequence that goes 31, this number, 63, 8, no solutions. That's a fun solution. Yeah, that's this sequence. Does this skip out? Or 1 if n is a square. Okay, so filled in the gaps. So surprisingly large numbers like that one, which is what we saw over here somewhere. Yeah, good. Okay, love this. Okay, good. Hopefully we don't have to calculate this one in an exercise. Quick look at the exercises. Oh, I see now where we're doing 13 and 19. They've got interesting continued fractions that go on a bit and give surprisingly large values for their fundamental solution to x squared minus my squared is 1. Is 29 bad as well? Let's have a look in the table. So, cheating a bit for the exercise, but is 29 bad? Yeah, 29 is horrible. Okay. Okay. Let's see how this book works. This book they could have picked any number to put in the exercise, but they'd already used 13 because look, the answer is this. They'd already used 19 because the answer was that. Could have done 22, but no, let's put 29 as the one in the question. That's great. Oh, brilliant. Right. Murray says it's time for a cup of tea. We're going to look at question 3 but not do it, and then we're going to make a cup of tea, and then it is time for chapter 5, I believe. Show that every positive integer that is not a square can be expressed as a quotient like this, n squared minus 1. Whoa. Every positive integer that is not a square can be expressed as a quotient for suitably chosen pair of integers n and k. And in fact, there are infinitely many choices of such a pair. Why do we exclude squares? Well, let's rearrange it. So what was this? Show that. Let's rewrite this. So that's 2 cups of tea. I really thought I had a cooldown timer on them. Problem. Given q, not square, there exist n and k such that, and then I'm going to write n squared minus 1 equals k squared q, and then I'm going to rewrite it as n squared minus q k squared equals 1, and I'm going to go, that's the thing we've been dealing with, that's Pell's equation, with all the letters have been changed, but you can rewrite this as finding n and k, finding x and y such that there's this, and we've already decided if it's not a square there aren't any solutions. I don't think we've proved that there are non-trivial solutions. My trivial solution would be 1, 0, and you're really not supposed to put 0 in here. 0 over 0, that's equal to your number q, right? What's for squares? No, absolutely not. Yeah, so I think we're trying to prove that this has got infinitely many. Oh, did I get my n's and my k's wrong? Oh, okay, maybe that's a good point. No, that is a good... No, I think this is in brackets. I don't know, it's kind of aligned like it might be upstairs. It doesn't quite look like n squared minus 1 over k squared separately to me. Don't know. Have you ever seen 40 cups of tea on a desk? No, why would you make 40 cups of tea? 40 cups of squash, yes. 40 cups of tea, hard to keep them all at a consistent temperature. Make an urn of tea if you need to give 40 people tea. It would actually be false, wouldn't it? Because n squared would be a square. 1 over k squared would be some tiny fraction of a number. It'd be quite bad. Okay, right, good. So I think this question is a little bit like, right, okay, like prove the thing that we're going to do in chapter 5. I've rearranged it into a different thing. Do I care about this? You can express it as a quotient. Suitably chosen n and k. No, not a lot. Okay. Bit hard to drink. Well, yeah, you get it out. Yeah. Tea being too hot is good. Right, okay. I'm going to make a cup of tea. Because 2 different viewers have told me that I have to. So we're going to do that. Looking at the notifications reminds me that M Peacock Music followed. So thanks for the follow, M Peacock Music. Good username. Right, it should be some sort of perk for choosing the mug, right? As long as we're not making it weird. Right, okay. I'm going to make that tea. Be back in a minute and a half. You won't miss anything if you go away for a minute and a half and make your own cup of tea or glass of water or whatever you do. Right, good. Okay, back soon. Bye. back, but only with 1 cup of tea. So possibly I'm supposed to work out how to refund this. Oh, I don't know how to refund a thing. Right, we're doing our best. Now there's a thing over there as well. Never great. never great after the outbreaks. In terms of Twitch. Right, okay. Well, yeah, you redeemed first, but I haven't switched mug. I'm on the Pashina mug today, which someone noticed before. It's maybe more cute than it should be. It's not the one I took into work. Right, I took 10 grams into work. It's like, maths. Look, ooh, patterns and puzzles. I did not take it in the Pashina mug. You've got to make a choice, right? When you go to a new place of work and there's an expectation that lots of people drink tea at work, so you take a mug so that you can join in. Which mug do you take? Oh, tricky. Totally got away with the Pashina one. Right. Okay. Right. Enough mug chat. Let's look at good. Chapter 5. Good. Right. Okay. I'm actually going to do a quick check. There's something confusing me because I'm just asking my own stream what's going on. There's 8 chapters in this. It doesn't feel like. So this is the website. The 4 types of forms, exciting. Equivalence of forms. Class number. Oh, that's good. I'd like to know what the class number is. Charting all forms. That does sound like a good place to go. Oh dear. And then we're still representations by quadratic forms. I've got a proof of quadratic reciprocity. So chapter 6 is maybe exciting as well. 7, I really don't know if I'll still be going for chapter 7. New Year's resolution or no. And then 8. Oh my goodness. Right, okay. Trying to decide how many chapters we're doing. I've been excited to get to chapter 5, but then, here we are. Is this one of those ones that gets much, much harder just as you were learning the things you wanted to learn? I found some of the proofs in this book before slightly tricky because of their topological reliance. They say that this triangle goes over here, and if you turn it over, then its 3 sides are still there, but the other way round. I found some of those quite tricky to follow and hard to work out what they're telling me. But maybe these are all different because I think this might be everything's along the line now. So maybe we're just gonna look at transformations along the line. Maybe, I don't know. Let's find out. Book is called Topology of Numbers. Right. 4 broad classes according to the signs. The signs of the values. Okay. At least one of the coefficients is non-zero. Okay, fine. That would be a 5th sort, the least interesting quadratic form ever. 0, 0, 0. Always assume that xy is not 0, 0, so that we don't get the value 0. Okay. I guess we're looking at coprime pairs. Anyway, whatever. Mostly I'm looking at coprime pairs for primitive solutions. Okay. If this takes on both positive and negative values, but not 0, except at 0, 0, then we call Q a hyperbolic form. Example, x squared minus 19y squared. Easy. Things we were just looking at. And some other, like complete the square, move it around a bit. Maybe there's an xy term in the middle. If it takes on both positive and negative values, and also the value 0, then we call Q a 0 hyperbolic form. Example, x squared minus 25y squared, because that can be 0 if you put in multiples of 5, 1. Yeah, okay. If qxy takes on only positive values or only negative, then we call it elliptic. Oh right, example like an ellipse, x squared plus y squared. Circle. If q takes on the value 0 and either positive or negative values, but not both, then q is called a parabolic form. Example, just x plus y all squared. thinking about parabola or something. I'll pick a weird one because that can be 0 if x is 3 and y is minus 3. But it can never be negative. Okay. So, right, okay, motivated in part by the level curves. Yeah, okay, you should equal to constants. Desmos 3D or something, slice it up, see what you get. Do you get ellipses? Do you get hyperbola? Do you get parabola? Okay. Ellipse goes 3. Oh, no, not parabolas. Oh no, they got me. Straight lines. Conic sections. They got me. What's going on there? So I guess these are actually, I want to call them linear forms because I realised that if you have this, then x plus y is either plus or minus constant, root constant. So straight lines. In my example anyway. Right, okay. They got me. It was on screen, so maybe you saw it before me. But they got me. I thought, I have level sets. Off we go. Right. Another feedback one can pass from hyperbola to ellipses through a transitional case of a pair of parallel lines. Yes. That needs an animation, so I'm going to quickly put that expression in Desmos. Oop, hello. I think so the transition that they're talking about is this thing where it can stretch through, in this case, parallel lines. Maybe I wanted a minus sign in there. No, that wouldn't help. There you go. Yeah. Desmos, go. Parallel lines for me. What do they say? Oh yeah, that's what they say in the text because that's true. Much simpler than other types. So if c equals 0 in the middle, then you get parallel lines because this says x squared equals 1. Okay. Other constants are available, so I kind of feel like maybe I should be changing this constant on the right as well. A bit like a separate slider to say, oh, separate constants. No, that's still my C slider that I've grabbed. Other constants are available, so maybe I should do that. That's just going to be a bigger picture, isn't it? Cool, okay. I'm sure math tutors do, or do some sort of more exciting Desmos version or something, but you know, there you go. That's my very quick Desmos for these parallel lines. I was expecting, this is stupid, I was expecting crossing lines because I'm thinking still about the level sets of a hyperboloid thing. Hyperbola. Come on. That's not what these are. There's some special level sets of one of those. I suppose that's the 0 hyperbolic form. Might have a particular level set that looks like crossing lines. Places where it's 0. I mean, we're plugging in integer values, but I'm going to call them lines anyway. Join the dots, fill in the reals. That's what I meant about like the direction 5, 1. Or I suppose 5 minus 1 for my example of that one is x squared minus 25y squared. Because you can go sort of multiples of 5, 1 will give 0, but also multiples of 5 minus 1 for a different direction. So that would be a lines like this really wide x would give 0. And there's lines over here. I mean, I'm going to draw it for reals, but you get the kind of saddle point like this with a wide x. That one needs a Desmos. So we're just going to look at the level sets of, very quickly, this expression equals, so 1, 2, 3 look like that, 0 looks like this pair of lines, and minus 1, 2, 3 looks like that. I slightly wish I'd picked a smaller square number, but here we are. So you have graphs like this. Yeah, I'm going to switch it for a smaller square number and hope that nobody notices. The smallest square number. Good, you get a thing like this, but stretched out by some amount. So some points where it's positive, some points where it's negative, and if this thing, if this thing is a square number, then you get integer points. You kind of, for the reals, Desmos does reals, right? So for the reals, you always get this x, whether or not the x goes through any rational points. It's to do with whether its gradient is rational or not. Yes. whether its gradient is rational or not. I had to do both directions quickly. Yes, good. Okay. And its gradient is, for those straight lines, is of course the plus or minus square root of this thing here. Okay, so if I put 3, then this does go through points like 1, root 3, root 3, 1, come on. That does go through that point, of course, but it doesn't go through any rational points, and especially not any integer points. Cool, right. Okay. Yes, we're going to look at the discriminant later in the chapter. They're still doing that thing. It was saying later in chapter 5. We're in chapter 5 now. You can do it. It's fine. I made it to chapter 5. You can now tell me. Tell me why it's true. We're in chapter 5. We're not going to be in chapter 5 forever, or we've got to prove everything. Okay. Good. Now we'll look at the determinants. There's a square number hiding in here. Good. Okay. Yeah, that makes sense, I think. Right. Natural question to ask is whether every integer occurs as the discriminant of some form. Oof. Is that okay? B squared minus 4ac. This is congruent to b squared mod 4. A square such as b squared is always congruent to 0 or 1 mod 4. So you can't make every number mod 4. You can only make things that are congruent to 0 or 1 mod 4. Can you make all of those? The simplest ones. If you're looking for a multiple of 4, put the k here and the discriminant. Well, there's no b's here. Minus 4ac will be 4k. Oh, good. That's multiple of 4. Any multiple of 4. And then this one, oh my goodness. So what's the idea here? The idea, I think, is that this b squared could be 1 if you set b to be 1, and the 4ac you could do the work of being 4k. So if you want something that's 1 more than a multiple of 4, well, that's a multiple of 4, and maybe that could be 1. I mean, it could be loads of things, but maybe it could be 1. So this quadratic form has discriminant 1 minus 4k, in a way. 1 minus 4k. Okay. 1 minus 4 minus k's in a very pedantic way. 1 minus 4, 1 lots of minus k. I'm getting too much. Okay. These are called quadratic forms, which I realise now is quite similar to the phrase quadratic formula, but it's not those. Oh, I forgot to tell you, while I was making tea, I realised a link to Oxford Online Maths Club. I shouldn't really do this because it's crossing the streams a little bit, but on Maths Club we thought about formulas for the Fibonacci numbers, and something someone said right near the end was a really efficient algorithm for calculating Fibonacci numbers. You only need to store 2 numbers in memory, the 2 things that you just had, and then that's enough to work out the next Fibonacci number as the sum, and then so that you can work out the next one, you should keep the bigger thing that you were just using, but you could throw away the small number. So you keep the big one, you throw away the small one, and replace it with the sum. I guess first you work out the sum, and then you do that throwing away and placing this new thing there. And of course that's now larger, so the next time you're going to throw away the other one. So the code that they suggested on Maths Club in chat was something like alternate between throwing away the left and right ones. That's exactly, and maybe it's why I was thinking like this, it's exactly the thing I was describing about working your way through this binary tree. That if you make alternating choices, right, left, then you head towards the golden ratio, and you're doing the continued fraction for the golden ratio, which alternates left and right, just 1 of each on each side. So in general, if you can use the same code, almost, to calculate other numbers, other irrational numbers, by overwriting either the left one or the right one, A or B, in your code, following a pattern given to you by the continued fraction. So the instruction just needs to change whether you overwrite the left thing or the right thing each time you work out the sum, and that gives you a sequence. So can we turn that into a formula? Anyway, never mind. So then maybe you could do all of this in terms of the same language that we use for Fibonacci numbers. Yeah, sometimes we end up talking about the same stuff by mistake. Maybe that person's got a point on YouTube, but maybe this is all. Maybe everything is helpful for everything, right? Maybe this is helpful for Matt just because thinking about stuff is helpful for Matt. I don't think it's the most helpful thing for Matt, so I'm going to stop talking about Matt again. Right, here we are then. We're looking at the 4 types of forms, which I can just about remember. Hyperbolic, zero hyperbolic, elliptic, and parabolic. Just about remember it was a page ago. Oh look, here's the diagram like the one I had. This is going to be a good day. Preliminary observations. In the arithmetic progression rule controlling the labelling of the four regions surrounding the edge of the topograph, an edge of the topograph. Okay, so the topograph doesn't itself have edges, it's a binary tree. It doesn't have an outside edge or something, it just keeps going out with this little branch-like tendrils. There's a common increment. Okay, good. Yeah, I could have had a name for this, couldn't I, before? For these things where the difference was equal. I called them A, B, and C instead of P, Q, S. But yeah, okay. So H, we're going to label it on the edge, really? The direction in which the progression increases by H. I guess you could show it on the edge. That edge, the edge uniquely gives you a section of the binary tree like this, and then you work out the form. Yeah, who's Matt? Good question. Who's Matt? We don't know Matt. Sorry, I missed that. That was way too slow of me. Sorry. Good job, chat. Changing the sign of H corresponds to changing the orientation of the edge. Okay, so okay, fine. The sign. You have to tell me you're going this way. You're looking at the arithmetic progression going this to these to that. It's a strange rule, isn't it? Okay. Very special case. 0, fine. Okay. The values of the increment H along the boundary have the interesting property that they form an arithmetic progression. Right, okay, there's your quadratic sequence. The differences or something form an arithmetic regression. And the amount that it increases is 2p, where p is this one that is shared. So we saw this for 1. I suspected for the -1 that it would be the other way round. And in fact, this is always true, that these things go in an arithmetic progression. There's a kind of second difference thing going on here for your quadratic sequence. Never mind. Okay, we call this the second arithmetic progression rule. Okay, it's more of a quadratic rule, but fine. Okay, second arithmetic progression rule. Start with an edge labelled H, with the adjacent figures labelled P. The original arithmetic progression rule then gives you the value P plus Q plus H and P plus Q minus H. Yeah, fine, okay. So then we're looking at the difference of the differences or something. We've got here some value, P minus Q, which is different from H because, yeah, okay, fine. I don't love it, but yeah, okay. We've done this sort of calculation in passing. Must be H plus 2P. Oh, we're looking over here in this text. Okay, I just believe this because we did a good example, and yeah, I'm very susceptible to this kind of fact being true. Yep, okay, repeated applications, we get an arithmetic progression. Another thing is the monotonicity property. Oh, here's the tree coming off maybe the separator line or something. It's justifying that as you go up the tree, away from the separator line, you don't get any more ones. It's not what we care about, or anything small at all, you get larger things. The figure at the right, if the three labels P, Q, and H adjacent to an edge are all positive, so we sort of had this, didn't we? Because we had a sort of maybe a separator line going down here, I think, and negative stuff on the left. We were interested in how this continues out there. And so all the three labels for the next two edges, and the new labels are larger than the old labels. And in fact, I think if these things are positive numbers, then these differences look like they'll turn out to be larger. And I sort of just believe this by just chasing the numbers around from the original arithmetic progression rule. Yeah, okay, good. Right, so this is larger, and actually quite a lot larger. And then this difference is getting larger. It's not the same on these two branches, but okay, we're just going to keep getting larger and larger numbers. In fact, the differences are increasing. Yeah, fine. Okay, good. Oh, hello. If an edge is labelled H with adjacent regions labelled P and Q, then the discriminant is H squared minus 4PQ. That's quite fun. That's a good link. I assume this is going to be true just by thinking about the values on, yeah. Okay, so H is something to do with the difference between what would happen if you plugged in the mediant versus what happens if you plug in these numbers. So I imagine it's just a bash. Yeah, okay. Sine of h and the orientation of the edge. Yeah, okay. Yeah, this is going to be an algebra bash, right? There's a square down here, so this paragraph is going to try and convince me. For the given form, the 1, 0 and 0, 1 regions are labelled A and C. Why do I care about those ones? You want to convince me in general, right? So maybe, assuming it's constant, the thing is sort of the same everywhere, we might as well look over here. A and C, and the edge, yeah, because the next one, the median rule, you add the numerators and denominators to get the next one. It would be 1, 1, where you get A plus B plus C, so the difference in that arithmetic progression is the increase by B, so H is B. Yep, good. So what have we got? The discriminant should be b squared minus 4ac, but that would be then h squared minus 4, and instead of these values, ac dq. Okay. Other edges we proceed by induction. Oh, does this sort of stay true as we go through the binary tree? Here we go then. I have to keep remembering that everything's connected, that it's not just, so it's like that proof, the monotonicity proving there are no other solutions, which I think I now believe, so that's good. No, I don't believe in the separator line yet. I believe that going away from the separator line won't give me any more solutions. I don't believe that the separator line yet. I don't fully believe that it's a thing. Okay. For the inductive step, suppose we have two adjacent edges on here, labelled h and k as in the figure. Suppose inductively that the discriminant is this. We have r is p plus q plus h. And from the second arithmetic progression rule, we know that k increases by 2q. Hey, who's this? This is Scuff Dude. Thanks for the follow, Scuff Dude. Welcome to Chill Maths. We're learning about continued fractions. Thanks for the follow. At some point we're going to switch to Wikipedia because we have a long-running thing to try and reach 315. 315 is the smallest number that doesn't have its own Wikipedia page. And possibly when we get close, I might try and create the Wikipedia page for 315 to try and push the boundaries of knowledge to the pushing it towards infinity. That's the plan. So thanks for following. It does push me towards maybe having to make a Wikipedia page. We are going through Hatcher's Topology of Numbers, which is a free book that you can get on that link. You can download a PDF. I think you can get a physical book. I haven't checked. Do I agree that there's an infinite line of positive values and an infinite line of negative values? Yeah, I suppose if you keep making x larger, then you'll get lots of positive values, and if you keep making y larger, you'll get negative values. So I suppose maybe I do believe that somewhere in between there's a separator line by, I don't know, intermediate value or something. Look in your binary tree and just, what do I believe, that they're all positive? No, because the binary tree at each level has got some stuff going on. Yeah, fine, okay. I mean, the book hasn't convinced me yet. Maybe Twitch chat has convinced me before the book has convinced me. Good. Yeah, so we've been reading this book, but only on Twitch. My rule, I'm not sure if I've discussed this, but my rule for myself is I'm trying to learn what's in this book. Not necessarily understand all of the content properly, but I'm trying to learn this book a bit. But I'm only doing it on Twitch for 2 hours each Sunday. I don't read it in between streams. This is not a very good way to learn maths, really, but here we are. Right, okay. we were just reading about the second arithmetic progression rule, which tells us that this difference goes up. And our challenge is to check that this thing squared minus 4 times these things, which would be another version of h squared minus 4pq, read across this edge, is still the same determinant. So I suppose I could read the book in between streams, but partly I don't have a lot of spare time in between streams. And partly I like the fact that the streams put together, I mean, they really wouldn't make sense. They hardly make sense anyway, but they really wouldn't make sense if I came back and said I'd done some off-camera understanding, which is I think what they call it in Minecraft streams, where you come back and the Minecraft streamer has got like loads of diamonds, they've been on adventures, and you think, what's happened here? So to keep it pure, we're doing all of the understanding very slowly during chill maths live streams. Yep. Yeah, also time management. Right, they're just going to enumerate, they're just going to plug it in, work it out. K is this expression, 4 and then QR. Do we know something about QR? Yeah, we know R because of the median rule. We're plugging in. What are we doing? So first arithmetic progression rule. We're no longer even really evaluating quadratic forms. We've got a trick for it now. The first arithmetic progression rule. So that just goes in here, and then the dust settles, and it's turned out to be h squared minus 4pq again. That's not a very satisfying proof, is it? There's some algebra going on. Do I want to work out what's going on? Not really. So you could combine this together with our proof of the first arithmetic rule to say, no, I want to get down to like raw metal, like what's underneath, what's the kind of base ground level of what's going on here, which means remembering what the binary tree means, remembering where the arithmetic progression rule comes from, which is just about looking at values of the quadratic form and knowing that we're looking at the median for what's next in the tree. Yes, we're in the version now where regions mean fractions, and the lines we're looking at are boundaries between neighbouring things. Like, yeah, I've been thinking of it as binary tree that goes from these two. Maybe I've now tricked myself into thinking about the dual graph and I've got confused the other way around. That'd be fun. It's been a graph for a while, and now we're looking at the dual graph. I find that hard. Yeah, so each edge, I have tricked myself into thinking about the dual graph. Each edge represents the pair of numbers that we're holding, and we have a choice. We can go left and keep holding this one, replacing with the sum, or we can go right and keep holding the right one and replace with the sum. So that this branching process thing is describing the process of throwing something away and replacing it with a sum, which you can do if you follow a pattern. You will converge to a particular irrational, better than that, a particular root of a non-square integer, if you follow a pattern on your way through. It'd be a root of a very particular sort of quadratic. Okay. Right. So what was this section? Because it says elliptic forms down here. We've just been doing some general properties, and now it's time to look at elliptic forms. Look at these forms first. Recall that we defined a form like this: elliptic, non-zero. These are the good ones, I think. We like these ones. They include Pell's equation sort of shaped things. Okay. Yeah, you can switch by putting a minus sign. Good. Always assume we're in this case taking positive values. Okay, good. We also generally assume when we look at the top graphs of elliptic forms the orientation of the edges is chosen so as to give positive h values. Okay, fine. For a positive elliptic form Q, bit of a mouthful, that's what we're now looking at for Pell's equation shaped things. P be the minimum positive value taken on by Q. We would like to know if that's 1 or not, I suppose. Probably is going to turn out to be 1, isn't it? Oh, there's no statement about this thing having coprime things going on here. So it could be like 19x squared minus 19y squared. That'd be a bit of a problem. Xy must be a primitive pair, otherwise divide by that and take a smaller positive value. Definitely positive, yep, it would just be divided by the factor. Thus, there is a region in the topograph with the label P. Good. All the edges having one endpoint at this region. Oh, including these ones going away, or the ones going away, must be oriented away from the region. So hopefully this is going to be the number 1, but I'm no longer really convinced by the arithmetic progression rule. The orientation now has been set to say, my goodness, this is the smallest thing. And then you've got 2 medium-sized things. So that has to be larger, so the arithmetic progression must be increasing. Okay, now you've got 2 of them and they're bigger. This is the smallest positive value. Oh, it takes positive and negative values? Yeah, what's going on here? Elliptic form? Positive only takes only positive or only negative? Oh no, these elliptic forms are not. These are the ones of the form x squared plus 19y squared. Elliptic forms. I got confused. Right, okay, I don't really care about these. Or maybe I do. Primes of the form n squared plus 1 is quite exciting. A few live streams ago I said something that's not quite true about... I should remember this in the t-shirt picture, which I still need to get printed on t-shirts. But yeah, so still I use some t-shirts or something. I had a throwaway comment to say along this line, so this represents Gaussian primes. The circles that are just one colour are Gaussian primes. The real axis goes along here, the imaginary axis goes along here. So some real numbers survive as primes, like 3 and 7 and 11. Along this line, I sort of said in passing that there are infinitely many primes along this line. That's actually unknown. There are some, like 1, 2, 3, 4 of them along here, but it's actually unknown if there are infinitely many primes of the form n squared plus 1. So we just don't know, which is crazy. We also saw the cat, yes, love the cat. Right, we got some, pictures. Also, Rex put a picture in Discord that I'm supposed to use as an emote. So maybe I should use my 2-week break to update all the images and things. Streaming. The cat's very good. I'm very proud of the cat. Right. Okay. Also oriented away from the region. Monotonicity. Yeah, I think we saw this. That the differences would increase by S and by R as you go out. So you have H here and you have H plus S, H plus R. Okay. So we've got this minimum value. Okay, right, okay. So I'm now on board. We're thinking about something like x squared plus y squared or something, which has minimum value 1. That's boring, isn't it? That's been 3 and 4 or something. Still feel like I know the minimum value of these things. It might not be like that. It might have some sort of cross term in the middle. And now maybe this is more confusing. I think that's probably still... I should take the discriminant, shouldn't I? 4 squared minus 4 times 12 is very negative. 2 squared minus 4 times 3 times 4 is very negative, so I think this is still a elliptic form. Not obvious what its smallest integer value is when you plug integer pairs in. Is it obvious? Not obvious, I think. Maybe putting in 1 minus 1 would be a good idea, because then you get some negative 2 in the middle here, as well as these positive terms. But putting negative 1 in, and you get 4 off this term, wouldn't you rather have 0? Might it just be 3? You can imagine some sort of trade-off there between having, you really don't want any y because the 4y squared, or maybe you want a little bit of y so you get some negative stuff going on in the cross term. If I change the sign here, then it might be positive numbers that are good. Okay, right. Okay, so I'm now interested in the question to find the smallest value that this quadratic form can take. It's not obvious to me. I've forgotten whether we're looking at sort of something with no common factor between the coefficients. Can't remember if we're doing that, but maybe it doesn't matter. So I can see the very source edge down here, which sounds very exciting, so off we go. Okay, the H labels on these edges form an arithmetic regression. Fine. Okay, labels and edges, right. We're now labelling the edges again, which I feel is getting us back towards the territory of talking about, oh gosh, we're going to take like a joule of the joule and get back to where we were. If some edge bordering the P region has the label H for 0, then the topograph has the form shown in the first figure below. with the orientations. Let's go down here. Oh, I love the diagrams in this book. So if there's a 0, then you get something like this, which is quite fun. An example of such a form is px squared plus qy squared. It's a source edge. So all other edges go away from it. It can't be 0. Like a source edge, I think it might be the source edge. The other possibility is there is no edge bordering that. There's an arithmetic progression going on, so, and it's not the constant arithmetic progression, so there'll be some point where it changes positive to negative. Yeah, so you've got this arithmetic progression that it extends infinitely in both directions. So, you know, equation of a line, if you extend infinitely, that's going to go through 0 somewhere, maybe at an integer point or maybe in between. So you extend the values of this arithmetic progression out in both directions. Okay. Since the labels, yeah, must be some vertex where there's change the sign. So orient the edges to give positive age for labels. All 3 edges meeting this vertex will be oriented away. Oh, cool, this is the source of vertex. Okay. And again, I think it's the source vertex because everything is then running away from it. The 3 regions surrounding a source vertex labeled PQR. Then, oh no, here we go. Here are 3 inequalities. These are called triangle inequalities because that's where you've seen them before. They're edges of a triangle. Oh no, that feels like a coincidence. There's not secretly a triangle in here, is there? What do you mean, here we go again? This is bad times for triangles? We like triangle inequalities, don't we? Or no, maybe not. Oh no, I suppose is what I said when I saw them. Where does this come from? The fact that the 3 edges all point away from this vertex. Let's see if we can understand that. So, right, so the pointing means that the sum of these 2 is larger than r because there's an arithmetic progression increasing as you go away towards whatever this is, but increasing. P plus q is bigger, and then this is even larger again. So P plus q must be greater than r, and similarly symmetrically, or around we go. Never in that time. Right, good. In the case of a source edge, one of the inequalities becomes an inequality, a degenerate triangle. For example, r equals p plus q in the earlier figure. There's r in the previous figure. Oh, I see. So p plus q, but then the 0 means that you have a kind of constant arithmetic progression, p plus q, p plus q, p plus q across this shape. Wow, it's coming up with so much, this arithmetic progression property. So you could introduce the letter r and say that it's equal to p plus q, or read around this node. That feels like a slightly... Just because 2 numbers are equal, you could throw in a third one and say the difference between these 2 is 0. So this is like a triangle with 3 sides, one of which is 0. Like, you could, I suppose. As we know, any 3 numbers can be realised as the 3 labels surrounding a vertex in the topograph of some form. I've forgotten why that's true. Possibly you could think about, oh yes, so what's going on when you plug in 1, 0, 0, 1 and 1, 1? You just set up the numbers a, b and c to make this exactly what you want, right? So it's like px squared, that'll be good for this one. Qy squared, that'll be good when I plug in this, it'll give me q. And then panic slightly. Oh no, I want to get r minus p minus q in the middle here, xy. So that when you plug in 1, 1, I've cunningly cancelled off the p and q and given you r. Yes, so if these are positive integers satisfying the triangle inequalities, okay, then this vertex is the source vertex of an elliptic form. So in particular, this would be, if these do the triangle inequality, then this gives something with discriminant that's negative. Seems plausible. Let's just check the discriminant on this. This was just an example of how to do it, but let's check it anyway. Am I happy with this? A little bit, not very. Never mind. Okay. Yes, I want to see if I can link together this fact, right? which of the triangle inequalities do I need for this one? So let's go question mark. If, and then how many of these do you need? So I think this is negative because I think it's going to turn out to be, if you have all three of these, then I think this one is elliptic because I have my node here with three things coming out. If they satisfy these triangle inequalities, not obvious to me that that's negative. Right, well maybe I'll just go for it. Let's go for it. I don't really want to. Yeah, no, I don't think I will. I don't think I want to. They're all positive numbers, right? Maybe. Okay. Possibly I need to square some of these, and I'm not quite sure I can be bothered. Chill math. Let's go. Yeah, I'm going to leave that as a kind of thought. Right. For the source edges, P and Q determine elliptic form with the source. The situation source edge is simpler. Since any two positive integers P and Q determine an elliptic form with the source edge having adjacent regions length with P and Q, as in the earlier figure. Oh, that's like px squared plus qy squared was the example for that one. I think that is simple. Right. Okay. Hyperbolic forms. They always have a periodic separator line. Okay. Oh, have we gone past theorem 5.1 or section 5.1, theorem 5.2? I think it's all happening. Here we are. Oh, might lock in a little bit. Been waiting for this. It's chapter 5, section 5.1. It's been trailed heavily by the first 100 pages of this book. Then in section 5, section 5.1, theorem 5.2, we will prove a thing about periodic things. People of chat, welcome. Here we are. We have the claim that finally hyperbolic forms. Oh, you got to. This is not going to do well as a clip because I'm going to use all the words from the last 100 pages. The topographs of a hyperbolic form always have a periodic separator line, which corresponds to a periodic quadratic form, a periodic continued fraction for the roots of non-square integers. That's something we quite like. Better than just a periodic, better than just eventually periodic. There's also this link that the integer part is half of the final number that appears at the end, and the periodic part is symmetric. There's a bunch of symmetry things going on there because of how great the binary tree is, I guess. We got a proof now. So what do we do when we've got a proof? We try and work out how long it is. We try and attack it from different parts. Try and see what it reminds us of. Do our best to understand it piece by piece. Right. Let's see then. Let's read it. In the topograph of a hyperbolic form, the edges for which the two adjacent regions are labelled by what? The edges for which the two adjacent regions are labelled by numbers of opposite sign. That's the description of the periodic separator line, I think. Form a line which is infinite in both directions, and the topograph is periodic along this line, but other edges of the topograph leading off the line on both sides. Yeah, okay. I don't know why they've expanded out the phrase separator line, right? They've put the definition that's been sort of in here, right? Edges for which the two adjacent regions are labelled by numbers of opposite sign. All of that. That's the separator line. Okay. Here we are then, proof. So how long is this proof? It's the rest of the page. Looking at separating edges to try and build this thing. Only one separator line. Proof goes down half a page here, but there is a square down here. So let's skim what we've got. Skimming it. Must exist two regions of opposite sign. That's a good start. Edges where two adjacent regions have opposite sign. Separating edges, they've got to be in there somewhere. Follow it around to see if it splits and prove that it can't split, so it has to be just one line without itself branching at all as you follow, because the signs don't work out anyway. If they're all positive, then why are you looking over here? If they're all negative, then no. If there's a split like 2, 1, then you get the separator line will go along here and here, or along here and here. It can't do all three. You can't have three things where the sign varies between any pair of the three. That's not a thing. Okay, so that's going to be nice. Bit of argument. Monotonicity means as you move away, things are. I guess they keep doing this now to say you get to everywhere else. Once you've found some line like this, everything else. How do we know it doesn't stop? Oh, so this thing, it can't stop because when it gets to this point, if you've got some line over here, then this has got to be one side or the other. It can't be zero because we're not talking about a zero hyperbolic form. So it's got to decide. It's got to send you left or right. You've got to keep going. And it's binary tree, so you just keep rolling through. Okay, I like it. This is going to be great. Only one separated line. Remains to prove it's periodic. Okay, so now this is the proof that it's periodic, and this is going to be a kind of transformation fact, isn't it? Oh, doesn't look like it. Same direction. Okay, we're using this fact that the discriminant is embedded into the things as we go. Okay. Oh, right, it's bounding it. Oh, I thought weeks ago we saw that something was bounded by like some value, so there was only finitely much stuff going on. This is going to be the proof of how that works. Okay. Right, positive and negative. This is going to be good. Okay, that's the discriminant. So each of these things is less than delta. So you can't only finitely many possibles. That's a nice proof. Okay, I'm going to come back and read it again in a minute. Translation along there you go, and then it's going to keep doing the same thing again because your process just repeats afterwards. Edges on both because it's a binary tree. Everything's got degree 3. On both sides, it says on both sides, just a single region, and we know that doesn't work. Second arithmetic progression rule. I suppose that's a good thing to check. There isn't just one bit where it's negative. H labels along there with increments. And it's periodic along the separator line rather than. Once we know it's periodic, loads of things are true. Good. Okay, so it's periodic, and then edges leading away is this section down here. Right. Okay. So I've decided existence is good. It's kind of what Maths222 said in chat a while ago, which is like something like the existence of a positive and negative region, and then you're good. And possibly it's what they had in mind. I said something different about looking at the depth of the binary tree and sort of binary searching on that to find the point where it lives, but it's just better than that, which is just chase it along the binary tree and see where it goes. It can't stop, it can't branch, it's got to do just one thing or the other. Right, in we go. First part of the proof. There are 3 things going on. We're showing it's infinite in both directions, we're showing that it's periodic, and we're showing that it's got edges on both sides. Okay, let's read the proof then. Maths. The stream's called Chill Maths, but we're still trying. Thing I'm trying to demonstrate, I guess, is that when you're reading a maths book, it is nothing like reading a normal book. You don't just look at the words one at a time in the order that they're printed. We still chill. Yeah, let's go. Okay, for a hyperbolic form Q, all regions in the topograph have labels that are either positive or negative, never zero, because it's not a zero hyperbolic form. And there must exist 2 regions of opposite sign because so I've been imagining 0, 1 and 1, 0. There must be 2 regions of opposite sign. Is that a definitional thing for the hyperbolic form? Maybe it is. But it has to do both. Yeah, okay, maybe that's definition. We haven't done the thing about the discriminant yet, though, right? Was that just a sort of also a foreshadowing thing? Yeah, so down here we defined them in terms of whether they took the values or not. We will show later in this chapter that you can just look at the discriminant. So we're going to prove this for hyperbolic quadratic forms, but currently we don't know which those are. We don't yet know that those are the ones with discriminant that's positive. Right. Okay, here we are. Or is that, have we secretly done that in here somewhere? No, I don't think we have. No, I don't think we have. Proposition 5.1 about edges. No, I don't think we have. Fine, okay, so we're proving this technically at the moment. We don't know which ones these are. Right, okay. Good, here we go. Two regions of opposite sign, moving along topographs, joining two such regions, some encounter two adjacent regions of opposite sign. What do you mean somewhere encounter? Oh, this is actually a really strange start to the proof, right? It just says there's positive somewhere and there's negative somewhere, but it might be separated by loads of binary tree stuff. So you might have to go and find it. And as you walk between positive and negative, you will see at some point. I think you'll go for negative. So you can have three negative numbers around a point, but as you keep moving, eventually you'll see a positive number because there is one out there over here as you walk towards it. The thing's connected. I have to keep remembering that. I guess it's not obvious because you can't just start from 1, 0 and 0, 1 because this is a general thing, not specifically for Pell's equation shaped objects. Right. Easier for Pell's equation, then you would just put in 1, 0 and 0, 1 and say, oh, there you go. Right, okay. There's no walking between them because they're right next to each other. At the end of a separating edge, I mean, those two regions actually share a boundary. At the end of a separating edge, you do this. I liked this bit. Exactly one of the two edges is also a separating edge. Repeating this, keep going, infinite in both directions, and the edges lead to non-separating edges. Good. As you move off this line of separating edges, the values of Q are steadily increasing. Through positive inches, the positive side, negative side, so you never see any positive-negative interaction again. Only one separator line. Good. This sort of means that you could colour in the regions on your fairy diagram, a jewel of your fairy diagram. You could colour in the regions, and there would be, I suppose, a positive region and a negative region and a wheelie line between the two, separating them. So that doesn't sound that exciting. Let's not do that. It remains to prove that the topograph is periodic. Here we go. Assume all the edges along the separation line are oriented in the same direction. So this is a bit about finitely many values. Changing the signs. Yeah, okay, fine. Okay, if you read some of them off as negative numbers, please don't do that. Please use positive numbers. For an edge of the separated line labelled H, which I'm thinking of as positive, with adjacent regions labelled P and negative Q. So these are positive things, but there's a minus sign because it's a separated line. We know that H squared plus P, 4PQ is the discriminant. Yes, so this is about the edges related to the discriminant. We did some algebra, it was not that fun. Checking what happens as you move to the mediant. So if you like, that's about, you're doing the sum of these two fractions or vectors, the mediant sum of these two fractions, or the literal sum of these two vectors, and you're checking that the thing you could calculate between them for the difference in the values is related to the difference in the values of the quadratic form. Ugh, there's a quadratic expression going on. Good. P positive implies that this thing is positive. Oh, so that's a good start, isn't it? So this shows that all of the ones we're talking about have positive discriminant. Not yet convinced that every case with positive discriminant is one of the ones we're talking about, but I feel like I will be convinced of that very, very soon. Furthermore, there exists each of these less than 10. Oh, brilliant. Finally, many possible values or combinations of the values as you go along. For what's the value above, below, and the way it's changing. Since the separation line is infinite, must be two edges on the line that have the same values of all three numbers, because there's only so many possibilities, delta cubed options, uniquely determined by those labels, and then it continues. Good. Edges leading away because you can't just have one because of this second arithmetic progression thing. Yep, fine. Okay, good. Very nice. Good. I like that. I feel like that's proved a thing I wanted to know. Good. I'm going to read on a little bit. I'm hoping that we get the way to determine which is which before long. So I'm going to overrun a little bit. It's 4 o'clock, but I'm going to do a bit more chill maths. Let's make a quick plan for how that's going to go. There's parabolic stuff here. Some nice pictures with some zeros in. And some general conclusions. Here's the thing about the discriminants. So I sort of want to see this. Yeah, I think I want to see this before I go. And maybe this a tiny bit, and then there's some exercises, and then we're out of 5.1. Think about equivalence in the future at some point. Okay, more chill maths for overrunning. I'm going to skip. Oh, it's hard to skip stuff, isn't it? Let's skim through parabolic and zero hyperbolic forms because I feel like they're less interesting. Skim this. There's a couple of pages that we're going to read very briefly. Yeah, okay. Oh, it's all periodic. That is quite nice. That is very good, actually. It's not just the line, it's the trees going off it are the same. So you get the same values all over the place. It's kind of really solved that, hasn't it? For if you want some particular value, you can find it in a tree, and you know to stop looking if the values get too large. And then if you want to find another one, you just need to come down to the separator line, along the separator line, up the corresponding tree, and then look in there, in the same sort of place. So some transform down along the separator line as much as you like, and then up the other side, and you'll get the solution. If you want x squared minus 19y squared equals 15, I don't know if that has any solutions, but some other value. Right, okay, this is the correct way to join up. If you need to search through all of the integer pairs x, y, maybe this tree is a good way to do it. Provided the thing you're looking at is nice under the action vector sum. Throw away either or something. Yeah, the key idea is that we're moving from thinking about the values at 2 points to thinking about the vector sum of those 2 points. What's the value over there? And quadratic forms are surprisingly nice under that operation, it seems. Maybe that's how I would write this up. If I was doing a kind of one-page summary, I guess I've got to explain the binary tree thing to say why it reaches all co-prime pairs of points. Sorry, one pair of points that's co-prime. Whatever. Not skimming it. So I would skim things. Let's skim things. Yeah, these are less interesting. They play only a minor role. At least one region labelled 0, so you get this, whereas just H. You get this arithmetic sequence. Arithmetic progression, very nice. So if you can find that, then draw it like this. Oh, there it goes. Okay, right, lovely. Oh, is it a 4Q? 9Q and 25. Oh, okay. You get the squares. That's the form is parabolic. Taking on only positive or only negative values to do with the sign of Q. You can have Q of 0, so we're not allowing forms that are always 0. Like this. Oh, that's pretty boring. Okay. Periodic along this separator line because look at it. In the remaining cases, the label H on the edges bordering a 0 region is non-zero. The arithmetic progression of values label H on the edges bordering a 0 region is non-zero. It's quite a mouthful, isn't it? The label. So what was 0 about this one? Sorry. No longer skimming. I've started paying attention. It contains at least one region labelled 0. Each edge adjacent to a 0 region has the same label H. And from this it follows that the labels on the region do this. Oh, I see. So first case, if H is 0, is that this? If H is 0, you don't really need to label them, but then you would just get the same thing again and again. Boring. Okay, so this is the other case where you get these things. What's going on here? The label H is non-zero. Arithmetic progression, the values of Q adjacent to the 0 region is then not constant. So it includes both positive and negative numbers. So I feel like, okay, so these things are generally a quadratic sequence, but now we're in a kind of special case where we get this linear sequence. Fine. Which could be a constant sequence, very boring, or it could be this linear sequence. Fine, I guess. If the arithmetic progression includes the value 0, then you get a second 0 region. You get a source edge. Is that a source edge? Maybe not. No. What's going on here? Oh, yeah, it's not a source edge. The topograph is as shown. I don't know what to do with the separated line. I suppose it goes around here. Maybe. QXY with the two regions like this. So that doesn't look periodic to me. It keeps going. Okay. If it doesn't include 0, there's an edge separating the positive from the negative values in the progression. Extend the separating edge to a line of separating edges like we did before. If this extension does not eventually terminate with a second 0 region, the reasoning we use in the hyperbolic case would yield two edges along this line having the same h and the same positive and negative labels on the two adjacent regions, forcing the line to be periodic. This in turn would force it to be periodic in both directions, but no, since the line began with a 0 region at one end. Gosh, it's a bit much, isn't it? You can't have 0 at one end of a periodic sequence. I don't know what's going on there. A finite separator line. Oh, and here's an example. PQ and not coprime. That's kind of fun. This sort of puts it very far away. Here we must have Q bigger than 1. The regions not be adjacent, non-trivial fraction. The separation line follows a strip of triangles in the Venn diagram. I remember those. Corresponding to the continued fraction of P over Q, and then it stops. Since the separator line is dual to the finite strip, you plug in 0 somewhere miles away. But there's a fraction where you can plug it in and get 0. And also, there's a region straight away where you can get 0 by plugging in x equals 1, y equals 0. For example, like this, shown in the following figure. These ones feel more exceptional, don't they? Oh, they've drawn some triangles on for us. So here's a 0 at the start, and you can go along here till you get until you get to the region 2/5. It's got a rational root, I suppose. So that's what these things all have in common. They've got a 0 region. There's a particular rational number you can plug in that gives you 0. Sometimes 2. Okay, let's read the discriminant bit. And we're going to do it this way round, which seems hard, which is say, based on the values that it might take, tell me about the discriminant. So good luck, everyone. Here we go. Takes on only positive values. Okay, right, okay. It only takes one sort of values. That's our definition of an elliptic form. So it's changing Q to Q and Y to Q. It's not changing the discriminant. Fine, okay, whatever. Let's do the positive one first. The soft graph of Q contains either a source vertex or a source edge. For a source edge with the label h equals 0, separating regions with positive labels P and Q. That's a source edge, isn't it? If you have a label, if you have h equals 0 somewhere in there, the discriminant would be that, which is negative. Oh, right, whatever P and Q are. H being 0 would be enough. For a source vertex, we have, now here we go, positive labels P, Q, and R, because we're saying it only takes positive values. This is the elliptic sort. The edge between the P and Q regions, P, Q, and then over here P plus Q plus R. This thing is labelled H. It's P plus Q plus R. Is it? Oh, no. Regions having labels like this. The edge between the P and Q regions is labelled P plus Q minus R. Okay, fine. I guess it's pointing away from this. The arrow on this edge pointing away from that node is labelled P plus Q minus R for the difference between the kind of arithmetic progression things. This is going to branch outwards, so it's P plus Q minus R. So the discriminant looks like this. And then they've gone and done it. Yes, this was the thing I was scared to do earlier, isn't it? Oh, that's quite symmetric, actually. And then, oh, it's factorised like that. Using the fact that all three of these, yes, there's the triangle inequality. You're right, okay, they're using all three, was the answer to the exercise from about an hour ago. In the top right corner somewhere on the page. If you use all three, I could not see this factorisation. I think that is cool. Not really a factorisation, but this way of writing it down. Those things are negative by the triangle inequalities. But why do we have the triangle inequalities? the triangle inequalities at all. That's what source vertex. We said source vertex corresponds exactly to the triangle inequalities for those three numbers. So then we have the triangle inequalities and we can use them in this algebra to show that that thing is negative. Okay, parabolic form, we've worked out that there's some region 0 bordered by these. So h squared minus 4pq, well, the value is 0 and h is also 0. The edges are labelled 0, yeah, fine, okay. Parabolic forms seem like the worst ones. A zero hyperbolic form has a region labelled 0 bordered by non-zero things, but label h because they would be changing by. There would be h plus the value, h plus twice the value, but the value is 0. That's the second arithmetic progression rule. So this is h squared. Good. So zero hyperbolic form, finally good, okay. H squared. Which is the same everywhere. You can sort of do it by induction, reading across this diagram to work out what's going on in other places. For an edge in the separator line for a hyperbolic form, the adjacent regions have labels p and minus q, with p and q positive. So it's this which is positive. That's pretty good. Just look at the separator line and read off the discriminant. I'd forgotten it was the same everywhere. So its existence then tells us where to look to find a good example to see that the discriminant is positive. Oh, I'm going to prove it's not a square. Good. Right. Is it a square in? Yeah, so it's a positive square in that case, and this is the case where it's not a positive square. This is good. Okay. A must be non-zero, otherwise it would be 0. Yeah, okay. Hyperbolic forms don't do that. 0 hyperbolic forms do. Hyperbolic forms don't. If the discriminant was a square, then the equation az squared plus bz plus c would have a rational root if there's an x over y that you can plug in to that. You'd get x and y in here. If the discriminant were a square, you'd get rational solutions to this. Rational root. So this quadratic formula would then use your discriminant to give you rational roots. Thus we'd have this, and we'd have a 0 at that corresponding point. That is nice. Right, so discriminant square corresponds to rational roots. That's really good. Okay. You would have a value 0 at the corresponding vector in that way that I keep mixing up fractions and vectors. Again, impossible for hyperbolic form. Lovely. Okay, good. This looks nice. If an equation has one integer solution, then it has infinitely many integer solutions when q is hyperbolic or parabolic, but only finitely many solutions when q is elliptic or 0 hyperbolic. That is nice. That's really good. I really care about the hyperbolic case, I think, at the moment. I'm surprised. Oh, yeah, okay. When q is elliptic. Although, I can think of other proofs that you only get finitely many solutions when q is elliptic. Because, maybe not. If q is elliptic, then as you move outwards from 0, 0, you always get larger values as you go outwards. That's not very conclusive though, is it? Because I'm putting some big copine numbers and you haven't seen anything near the origin, so you don't know whether we're in the good bit or not. Will it need to get a larger value? Like x squared plus y squared equals 5, I'm not going to check large numbers in that. Something like that. I don't know. Okay, let's not prove it like that. Let's think about its lack of periodicity. And a monotonicity property implies that each number appears at most finite number of times. Because as you move away from it, things get larger. That makes me think it's a unique solution. Maybe I'm not imagining the monotonicity property correctly. Oh, there can be some 0 stuff going on. Yeah, you could have a bit of separator line for the 0 hyperbolic forms. And then monotonicity away from that. Good. If it had infinitely many non-primitive solutions, this would yield infinitely many primitive solutions, and that for certain divides this m of n. Right, okay. However, this is possible such integration of fixed M can only have finally primitive solutions. Okay. Right, okay, so they're worried about it. To really say it's finitely, you have to worry about non-primitive solutions as well. Over here, where we're looking for infinitely many, but hey, also throw in infinitely many non-primitive solutions, that's fine, or whatever. But here we're thinking about only getting finitely many. So finitely many would make a particular, reduce it down. There's only finitely many factors that you could be making in your reduced case. Okay, those are good technicality at the end to check, but I still feel like the elliptic and zero hyperbolic ones, yeah, not really. I do care about numbers in the form n squared plus 1. Who am I kidding? It's n squared plus 1, and x squared minus ny squared. Those are the cool ones. Okay, good. That feels like section 5.1, pretty much. I feel like we've classified these. Yeah, work out the discriminant of this one. Oh, crikey. Find the source edge or vertex, my goodness. Have we got any tricks for finding the source edge or vertex? I'm not sure we do. Not sure we do at all. Monotonicity, can we sort of find some and walk away from it? A nasty looking one as well. Yeah, I would explore, I think. Explore the binary tree, see if I can find. Maybe choose a vertex, work out as I go around that area. Are we getting closer or not? Don't love it. Yeah, well, how did the proof that there is a source vertex work? Oh, you find its minimum value and you consider what's going on around there. I don't know how to find the minimum value of these things. So, what am I going to do? Sort of want to complete the square. That feels cheeky, but just want to complete the square. And then its minimum value will just pop out. No, that can't work, right? It's got to be about integers. Yeah, okay. I'll stop trying to diagonalize it or whatever. If you can diagonalize it, then there's no mystery because it's the smaller of the two numbers. So I should just diagonalize it, shouldn't I? Who's going to stop me diagonalizing it? No one's going to stop me diagonalizing it, right? So my kind of feeling is that if I diagonalize it, then I'll find some eigenvalues. I should probably check that this works, but I kind of just want to find its two eigenvalues and claim that the minimum value is the lower of the two. This doesn't feel like it can actually work because when you diagonalize you have to do some division, and I'm not going to be talking about integers anymore, but that's kind of relevant. Maybe not. Okay, I'm going to write out this characteristic polynomial and then see how far I can take this. Well, I'm not enjoying writing out this characteristic polynomial. Do I ever enjoy writing out a characteristic polynomial? But here we are. So we've got a load of coefficients going on. Calculator time. Oh, could be worse. Could be worse. The constant term has turned out to be 21. We have lambda squared. And then we have an almighty sum, don't we? 92 plus 15. So 9 squared minus 97 lambda. Maybe I regret this. Yeah, maybe I regret this. Yeah, okay, maybe I regret this. Because that's got discriminant. Yeah, we're okay. I don't love it. No, okay, I'm going to abandon this as a thought. Yeah, abandon this. Go and explore the tree until you find something that looks like a minimum value. Keep looking around the smallest number you've got. Either you'll find a smaller number or you're actually at the smaller number and you'll get round to the source vertex or source edge. So it's the quadratic sequences we saw alongside. Do they come down and stay flat, or do they go down and through? Using the top graph of this form, find all integer solutions equals 60. Good. Exactly 4. 3 of which will be visible in the top graph. 3 of which, because one of them is non-primitive. Interesting. Maybe you should do this. I don't really want to do these numbers are so large. Why are they so large? Okay. Same value on two adjacent regions, then these regions are both adjacent to the source vertex or edge. The form is elliptic, or both lie along the separated line, and the form is hyperbolic. Ooh, same value on two adjacent regions. Same value on two adjacent regions. So I'd like to know whether the form is hyperbolic. So I've got some difference h along here, and I would like to know what's going on with c. So the relationship here is that h is 2a minus c. I care about c. I want to know if, so sort of show that h squared minus and then 4a squared. If this is positive, then we're in a hyperbolic case. That's what it means to be hyperbolic. Show that this implies that c is negative, or c is, let's go, we'll log a positive. It's probably the same in the opposite case. C is less than 0, or vice versa, if I have a negative or something. So that to me says I should be looking at AC or something. Maybe we should square this. Don't really want to square this. So I know that h squared is bigger than 4a squared. That tells me, I think, cases then, h is either bigger than 2a or less than negative 2a. Oh, that makes me think, yeah, okay. So this gives me h is greater than 2a or h is less than negative 2a. That's quite good. Okay, presumably the other ones are similar. But if this thing is equal to 0, then h is actually equal to 2a, so you get 0 over here or something. Is there a parabolic part of this question? Who knows? Anubis 72,000. Yeah, it's a math stream. We're overrunning a bit. I normally stop at 4 o'clock, but I'm taking a couple of weeks off after this, so quite keen to do some maths. We've got some exercises. We're trying to take them quite chill. I'm thinking about this textbook, which is all about number theory via this one weird diagram of all the fractions. So the subject is continued fractions and number theory, and the level is enthusiastic high school student or possibly undergraduate course. There's some overlap with that, but it's trying to do things without any prerequisites, except for the fact that I'm currently on page 127 because I've been doing this bit. Oh, Maths 2 to do is done at Desmos. Let's have a look at that. A symmetric fairy diagram. Oh, you worked out how to do the thing that's actually like a fractal. This is the picture on the front of the textbook. In Desmos. Oh my goodness, what have you done? What have you done? Oh, so powers of 2, right? Yeah, okay, good. So you put this asteroid in. There should be either a horizontal line or a negative or a vertical line. But the idea is that you keep splitting. Yeah, because there should be lots of triangles. Triangles. I will split this. I'll put it in horizontal, I think. I'll help. So what do I want? T0 between minus 1 and 1. Okay. So you get lots and lots of triangles. Lots and lots of triangles arranged in a kind of binary tree structure, where reading down here, there's a triangle linked to 2 triangles, and each one's linked to 2 smaller triangles, and on and on and on. Triangles. It's pretty good, isn't it? And upstairs there's another binary tree, and they're connected through the middle. I've never seen people do this before. The binary tree and another one, which is nice because then everything's got degree 3. Maybe I should look out there more for binary trees, but this is the one on the front cover. Very good work. Good. In particular, those regions being joined like a binary tree, and the regions being associated with particular fractions. Is that true? Yes, the regions being associated with particular fractions mean that we can visit all of the fractions. If we want to check all of the fractions, then we can visit them via exploring the binary tree. So here, our question on the screen is, show this quadratic form we'll talk about the values of this quadratic form, but values of the quadratic form, if x and y co-prime, correspond to putting a fraction into a kind of thing divided by y squared or something like that. Or I suppose if you have a fraction in mind with co-prime x and y, you can take out the numerator and denominator and plug them into this expression. I prefer that because then you'll get an integer. Region 1 on it also. Oh, you're gonna put the binary tree dual diagram on top. Is that what you mean? The diagram for the regions connecting triangles. The thing I'm trying to do with my mouse, right? Yes, if you can do that, that'd be great. We can have one maybe switch them on and off. Oh, yours just toggles with a single. It takes a while to render, but it's got all of them in one. All of them in one, rendered with one line of decimals, so you can toggle it on and off, which is quite nice. I guess you could put things in a folder anyway, but hey, nice. Dual diagram. Yeah. Should be alright. You have to generate a point inside each of the triangles, which is not obvious. Yeah, not obvious how you do that. At all. Maybe you get away by putting it. You have a marker for the midpoint. I'm looking at my second monitor, that's very rude of me. You have a marker for like the midpoint, so like down here, you just put it anywhere on this line. It's your marker, because all of this line above the point here, it would look good up here, but putting a point anywhere on that line would work. And similarly for this point over here, there's a fraction associated with that. If you put the marker anywhere on here, I guess you've got to be inside the circle, but anywhere on that kind of radius coming out to the circle arc. Point anywhere in there, because the triangle goes all the way in, so you should pick anything that goes in. I can't remember, are the circles all orthogonal to the outside? Is this just hyperbolic geometry? I can't remember. I think the circles are orthogonal. It doesn't really matter, does it? But yeah, of course they are. Of course they are. Yeah, you don't want angles at these points here. So I think these are all nice hyperbolic triangles, which is good. It's very hyperbolic sort of picture. Anyway, we've also got the word hyperbolic on screen, but not like that. Okay. So I'm thinking about this kind of repeated value thing. I've explored the case I care about, which is what's going on. You find the separated line if you get two things like this with the same value in the hyperbolic case. Minimum value of h for all the edges in the border of a given region, the topograph of an elliptic or hyperbolic form. What a mouthful. Occurs at an edge. I really think of h being positive and choose your directions or something, but okay. So the h things form an arithmetic progression. Oh, so mod h, arithmetic progression, is like a linear thing, but you put mod signs on it. It comes back up again. Having an endpoint that achieves the minimum distance to the separator line or source vertex. Oh my goodness. All vertices in the border of the given region. That one needs a diagram. Okay, not thinking about that right now. It seems too hard. Can we factor that as a product? Then q takes the value 0 at some pair of integers. Well, like b minus a. Yeah, like b comma minus a. Along one of the lines that make it up. Wait, so what's this one? Yeah, okay. Show also that the... Ooh, okay, we're going to show it 0 hyperbolic by showing its discriminant as a square. That seems fun. What do I know? I know that a is AC. I know that this lowercase c is BD, and that this thing in the middle is AD plus BC. So what have we got? The discriminant is AD, oops, not AB, plus BC minus 4 ACBD. And the question is to show that that's a square, but it is, because it is this square. Good, love it when a question comes together. Yeah, you worked out where to put points. Okay. I suppose if these things really are... Oh no, wrong way around. Yeah, tough. There's a bit of artistry there, I think. There's lots of points inside the triangle. You probably want something in the midline, but inside both circles. Oh, so if you're looking for something that's inside both circles, that's a kind of classic problem, isn't it? To say inside both circles, you know where these points are because you know the circles, and maybe you could choose the midpoint of those 2 points. You know, you have they're actually quite small circles for the ones that. Okay, so you have like your unit circle in this one, and you want something that's inside. There's this region that you want to hit. And actually you want to be on the line that joins the midpoints, I think. So you've got this interval here that you want to hit in the middle. Well, you know where these points are, because you know the radius is involved. So you know the distances. If these are progression along a line segment, lambda 0, 1, then you know these two fractions, big fraction in between. That's okay. Yeah, once you've decided you're on a line, it's a 1D problem, not a 2D problem. Okay, find a zero hyperbolic form such that 1, 5 and 7, 2 are 0. Well, that's this, but with 1, minus 5, 7, minus 2. Okay. Draw a portion of the topograph of Q, I'd rather not, that includes the two regions where Q equals 0. Right, because, I see, okay, so 1, 5 is somewhere in the binary tree, and also 7 over 2 is in the tree. Join them up. In that diagram, all the regions are labelled with fractions. This question says, work out where both of them are and show me all of the triangles that join them up because it's all connected. Good. Okay, I'm going to wait and see if Mathstudio2 can, well, you can put it in the Discord or something. Mathstudio2 is going to have a go at drawing this dual diagram we've been talking about for a while. Is the dual diagram the thing that they're calling the topograph? I'm going to double check that. I think it is. Yes, I'm going to double check it. Where's the first mention of topographs? It's back 100 pages. Well, load. Let's see. Topograph is on that page. Topograph. It was chapter 4, wasn't it? Next chapter. We've seen it now. Topograph. It was where we started getting these diagrams. Separate a line. Here's the topograph, just the dual. There they are. Here's the pictures that we've been talking about. The topograph. The dual tree. Okay, so that's the picture that Mathstudio2 is trying to draw in Desmos. The artistry being, oh, let's look at this one again. The artistry being in this triangle. Where do you put this point? Where do you put that point? Where do you put these points? Somewhere in the triangle. Looks like it could be the mid, but it's not quite. So not quite the midpoint of these points where they cross on a radial line. Biased towards the centre. I don't know how they've drawn this picture. It's part of the fun, isn't it? Is the topograph called the dual tree? The picture including the values of Q is called the topograph. Okay. Small amount of initial data, arithmetic progression rule. There you go. That was good, wasn't it? We did quite a lot with that. Okay, so that was about 20 pages. Let's jump here. Oh, perfect. Back in. Okay. This is quite a nice place to stop, I think. I feel like I've understood why these things have a periodic separator line, which corresponds to a lot of the nice properties that we had. There was also a reflection property at some point in there. Might need to go back and think about that again for some of them. Maybe not all of them. There was some reflection property, which explained why there was a link between the integer part and the last number in the periodic bit. It was your birthday. Happy birthday, Mary. Well done. You've got a year older. Well done. I hope you had a nice day. Hope you enjoy your birthday. Right, but I think it is time to stop doing chill maths. Next time, which will be in some point in the future, I'll try and update Twitch so that Twitch knows I'm on holiday. Not that I'm going anywhere, but on holiday in spirit. We're going to look at equivalence of forms in terms of these topographs looking the same. Don't all binary trees basically look the same? We're describing a binary tree, right? Okay. So possibly involving the values. If it takes equivalent values. Yes, okay. Then the values. Yeah, okay. So we've seen something about the values being the same. Different quadratic form, same values. Is it surprising that can happen? No, not really. X squared minus 19y squared is going to do the same stuff as y squared minus 19x squared. So I guess I do believe in equivalent. There are forms that are equivalent. Note here. But then lol, because it's not just that. Good. Oh, points. Right. Is this how we're going to wrap it up? Is this how we're going to wrap it up with points in? Oh, it's taking a while to load. Oh, it's got points. It's got points. They look like they're all inside the right regions. That's gone very well. It's a fairy diagram, but spotty. Final challenge is, I suppose, to join the dots. Oh, I do know the hierarchy of them. I guess you probably do, because you've got like this number. Oh, it'd be tough. I don't know how you would join them up. Join the dots time. Seems tough, because you've got a kind of binary tree structure, which is, well, I guess the point of this is it's quite hard to iterate over. But you've managed it for all the red lines. So I suppose if you can do all the red lines, well, you can do all the green. For this point, it's got to have two things coming out of it, and you know where they are, sort of, maybe. It's annoying that Desmos doesn't have arrays, perhaps. Just long vectors. This one feels like these ones. Okay, right. Okay, good. Including the 0 ones. I see we're in complex number mode. Of course we are. Love complex number mode. Right, good. Okay. We are actually calling it there, I think. To be continued on this fairy diagram picture, perhaps, if it's possible to get Desmos to join the dots. Did I show you my did I show everyone my Pythagoras tree, Desmos? You can do the Pythagoras tree. It's not that hard. Will crash my computer if I try and open it. Right. I tried to do a Pythagoras tree, but I realise now that this is going to render very slowly, especially because I'm running OBS at the same time. Uh-oh. Right, we're just going to see if that renders at all. Because I thought you could use these joining things, right, to scale on an F transformation and a G transformation to put in new points. So I've created these really long vectors for where to put the points. Yes, but then I have a button to press to do the next iteration, and if you do those, it calculates those very slowly, and then you can save it, but reloading it is really hard. So it should be drawing loads of squares. I think it's currently trying to draw thousands and thousands of squares. Oops. So maybe this will pop in at some point. I'm going to give it a minute. Right. Countdown from 10. See if that'll render. If not, I can't even use my controllers to reset it, right? So I've got these reset buttons to just put it 0, radius 1. I can't remember what that does. Whether it's a square or a diamond. There's some daft Desmos going on in here, with squares and diamonds being separate things, even though squares and diamonds are the same thing. It loaded. It loaded. Squares and diamonds. The Pythagoras tree is a fractal where you have a square at the bottom and then a little isosceles right angle triangle spacing it out, and on the other sides of that isosceles triangle, oh no, 2 copies of the Pythagoras tree. It popped in. There you go. Right. Enjoy your weekend. I'll see you. You know how this works. I will see you in, I think, 3 weeks. I think I'm back on 3 weeks. Yeah, back 27th of April, I think. Which means the YouTube releases will catch up with me. We've got a couple of weeks buffer for getting things on YouTube after the stream. Won't have that 29th of April. Right, cool. Okay, bye everyone. Take care. I'm ending the live stream.